unprecedented 16-year-long study using several of ESO's flagship telescopes, astronomers have produced the most detailed view ever of the surroundings of the monster lurking at our galaxy's heart, a supermassive black hole. The research has unraveled the hidden secrets of this tumultuous region by mapping the orbits of almost 30 stars. This is the ESOcast, cutting-edge science and life behind the scenes of ESO, the European Southern Observatory, exploring the far reaches of the universe with our host, Dr. J, aka Dr. Joe Liske.
Hello and welcome to the second episode of the ESOcast. Today we have a very cool piece of science for you. A team of German astronomers with characteristic precision and patience have spent 16 years mapping out the motions of 28 stars orbiting the very center of our Milky Way galaxy. Now, astronomers have believed for quite a while that the center of our galaxy is the site of a supermassive black hole. Black holes are a consequence of general relativity. They are objects that are so dense and whose gravity is so strong that not even light can escape them. These observations that we're going to show you today are the best evidence yet that black holes are not just theoretical constructs but actually do exist in reality.
Observers under dark skies, far from the bright city lights, can marvel at the splendor of the Milky Way arching in an imposing band across the sky. Zooming in towards the center of our galaxy, about 25,000 light-years away, you can see that it is composed of myriads of stars. This is a pretty impressive sight, but much is hidden from view by interstellar dust, and astronomers need to look using a different wavelength, the infrared, that can penetrate the dust clouds. With large telescopes, astronomers can then see in detail the swarm of stars circling the supermassive black hole, in the same way that the Earth orbits the Sun. The galactic center harbors the closest supermassive black hole known, and the one that is also the largest in terms of its angular diameter on the sky, making it the best choice for a detailed study of black holes.
So what this team did was that at various points of the past 16 years, they kept taking images of the very central region of the Milky Way. Now, from these images, they were able to map out the motion showed was that these stars aren't just moving about randomly, but that they are clearly orbiting a very massive central object. And the point is that this central object is completely unseen. Now, from the motions, it's also possible to deduce the mass of the central object. It came out to be a little over 4 million times the mass of the Sun. Now, what's more, that enormous mass has to fit into a tiny little volume. And so one cannot escape the conclusion that the central object really is a black hole.
The observing campaign started with observations made in 1992 with a SHARP camera attached to ESO's 3.5-meter New Technology Telescope, NTT, housed at the La Silla Observatory in Chile. More observations have subsequently been made in the last few years using two instruments mounted on ESO's 8.2-meter Very Large Telescope, VLT. Over the 16 years of this study, ESO's telescopes have stared at this one region for 50 full nights.
This new research marks the first time that so many of these central stars have had their orbits determined so precisely. The data also reveal a lot about the characteristics of these stars and how they must have formed. For one of the stars, the astronomers were even able to follow it for a complete orbit. The star approached the central black hole to within just one light day. That's just 5 times the distance between Neptune and the Sun. Professor R.Genzel from the Max Planck Institute for Extraterrestrial Physics in Germany is the leader of the team that made the discovery. Reinhard,
well, you see, the Milky Way Center is one of the most important laboratories we have to study in very great detail what's happening in centers of galaxies, in much more detail than we can ever hope to do in all other galaxies. Yet, here we are, we can study whether there's a central black hole, what happens around it, and so forth. All very general issues which you would like to explore and which you cannot really study that much in detail in other galactic nuclei.
Dr. Stefan Gillessen is the first author of the paper reporting the study. So Stefan, tell us, what's the most important result you obtained?
The most important result of our research really is that we have now empirical evidence for the existence of a massive black hole in the center of our Milky Way. The mass of this black hole is around 4 million solar masses, and we know the mass at the percent level.
This is of course an amazing result. But the team doesn't plan to stop here. Now in the past they've used the novel technique of adaptive optics to remove the blurring effects of the atmosphere. In the future they plan to do even better and to get even higher resolution images by using another new technique called interferometry. This is where you combine the light from two or more of the VLT's unit telescopes together. So Reinhard, what's the next step?
Well, you see, at this point we really are fairly sure that there is a massive black hole at the center of our Milky Way. And the next thing, we want to actually play with it. Play with it in the sense that we want to use it as a tool to test whether general relativity, the theory of Einstein, is actually wrong or right.
Wow, playing with a black hole to test relativity. That's pretty cool stuff. I'm Dr. J, signing off for the ESOcast. Join me again next time for another
ESO's
cosmic
Lassia
adventure.
Observatory, which is celebrating its 40th anniversary and became the largest astronomical observatory of its time, leading Europe to the front line of astronomical research, is still one of the most scientifically productive in ground-based astronomy.
In this episode, we're going to celebrate an anniversary. And quite an amazing one too. One of the most successful ground-based astronomical observatories in the world, Lassia, is turning 40.
With about 300 refereed publications arising from the observatory per year, Lassia remains at the forefront of astronomy. Lassia has led to an enormous number of scientific discoveries, including several firsts. The HARP spectrograph is the world's foremost extrasolar planet hunter. It detected the system around Gliese 581, which contains what may be the first known rocky planet in a habitable zone outside the solar system. Several telescopes at Lassia played a crucial role in linking gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, with the explosions. Since 1987, the ESO Lassia Observatory has also played an important role in the study and follow-up of the nearest supernova SN 1987A.
The Lassia Observatory is located at the edge of the Atacama Desert in Chile, one of the driest and most isolated areas in the world. This location is virtually free from sources of polluting light, and like the Paranal Observatory, which houses the Very Large Telescope, it has one of the darkest night skies on the planet.
At its heyday, Lassia was home to no fewer than 15 telescopes, among them the first, and for a very long time the only telescope working in submillimetric waves, the 15-meter CEST in the southern hemisphere, which paved the way for APEX and ALMA, and the Schmidt telescope, which completed the first photographic mapping of the southern sky. The telescopes at Lassia have also supported countless space missions, for example by obtaining the last images of comet Shoemaker-Levy 9 before it crashed into Jupiter. While some of the smaller telescopes have been closed over the years, frontline observations continue with the larger telescopes, aided by new and improved astronomical instruments. Lassia currently hosts two of the most productive 4-meter class telescopes in the world, the 3.5-meter New Technology Telescope, the NTT, and the 3.6-meter ESO telescope.
The NTT really broke new ground for telescope engineering and design, hence the name. It was the first telescope in the world to have active optics installed. This is where you have a set of pistons attached to the back of the main mirror. Now these pistons are computer controlled, and they constantly maintain the shape of the main mirror so that it can always produce the sharpest images possible. Now this technology was first developed at ESO, and nowadays it is used at the VLT and most of the current large telescopes in the world. In addition to active optics, the NTT's dome was also a revolutionary design.
The Lassia site was chosen after years of challenging prospecting, partly on horseback, in the Chilean Andes in the mid-60s by the first ESO Director General, Otto Heckmann, and several senior astronomers. In the following years, the site was developed and the first mid-sized telescopes were erected. Today, the Lassia infrastructure is also used by many of the ESO member states for targeted projects, such as the Swiss 1.2-meter Euler telescope, the rapid eye mount, and Tara gamma ray burst chasers, as well as more common user facilities such as the 2.2-meter Max Planck and the 1.5-meter Danish telescopes. The amazing 67 million pixel wide-field imager on the 2.2-meter telescope has taken many impressive images of celestial objects, some of which have now become icons of their own.
La Silla was ESO's first observatory in Chile, and was the start of a long and fruitful collaboration with that country and its scientific community. This is Dr. J signing off for the ESOcast.
The goal of current exoplanet research is the detection of a rocky, Earth-like planet in the habitable zone, a region around the host star with the right conditions for water to be liquid on their surface. The latest result from the European Southern Observatory comes closer than ever to attaining these goals.
Hello and welcome to another episode of the ESOcast. This time we have some very exciting news for you. It's another major ESO discovery. We'd like to tell you about the discovery of the smallest, or rather lightest, and possibly most Earth-like planet so far discovered outside of our own solar system. We'd also like to report on yet another planet within the same system that has now been shown to lie within the habitable zone of its parent star, meaning that it could host liquid water and possibly even life.
Gliese 581 is a seemingly inconspicuous red dwarf star located 20.5 light-years away in the constellation Libra, or the Scales. It is among the 100 closest stars to us and weighs only 1/3 the mass of the Sun. Such red dwarfs are intrinsically at least 50 times fainter than the Sun and are the most common stars in our galaxy. For astronomers studying exoplanets, red dwarfs are ideal targets for the search for low-mass planets where water could be liquid. Because such dwarfs emit less light, the habitable zone is much closer to them than it is around the Sun, which makes it easier to detect the planets.
Professor Michel Mayor from the Geneva Observatory and his team of European astronomers have carefully observed Gliese 581 over the past 4 years using the world's leading planet hunting instrument, the HARP spectrograph, on the ESO 3.6-meter telescope at the La Silla Observatory in Chile. Now what they found was that Gliese 581 is orbited by a planet that has only 1.9 times the mass of the Earth. This planet is known as Gliese 581e, and it is the lightest and most Earth-like planet so far discovered outside of our own solar system. Now within the very same system, the team also refined the orbit of a previously known planet called Gliese 581d. What they found was that this planet is definitely within the habitable zone of its parent star. Now what that means is that the planet is just at the right distance from the star for any water that might be present at its surface to be liquid. If it were any closer, the radiation from the star would be too strong and the water would evaporate. If it were any further away, it would be too cold and the water would freeze.
From previous observations, also done with the HARP spectrograph at ESO's La Silla Observatory and announced 2 years ago, this star was known to also harbor a system of 3 super-Earth planets. With Gliese 581e, the planetary system has 4 known planets, with masses of about 1.9 planet E, 16 planet B, 5 planet C, and 7 Earth masses planet D.
The planet with the largest orbit in the system is Gliese 581d, and it takes about 66.8 days for one round trip around its parent star. Now, because it orbits within the habitable zone of its star, this planet could be covered in liquid oceans, making it the first serious water world candidate.
Thanks to Mayor and his team, we now know that the Gliese 581 system contains at least 4 exoplanets. These planets were discovered through the tiny wobble they cause to their host star as they move around, only about 7 kilometers per hour, which equates to brisk walking speed. The discovery of Gliese 581e and the refinement of Gliese 581d's orbit were possible only due to HARP's unique precision and stability.
Using the HARP spectrograph, Michel Mayor and his team of European exoplanet hunters are leading the way towards answering some of our most fundamental questions about life outside of our own solar system. They are confident that in the not-too-distant future, a truly Earth-like planet will be discovered. So stay tuned.